Today we're going to write a simple script to take a bunch of straight lines, assuming they're simply supported beams, and show the shears, bending, and deflection plots, where you can change the scale and see some results. 52 millimeters, for example, 45 kilonewton meters for bending, and 30 kilonewtons for shear. And you can obviously just select any line for this, and you could change the load and the beam size used as extensions to this, and you could also set up formulas for fixed end moments and other beam types, not simply supported but fixed or others. And a reminder, you can get more tutorials like this at our website, and you can also download some of the scripts in this area here, and we've got some demo scripts you can test out as well. And feel free to have a look at some of our other services. We've got model conversion, rapid framing from architectural models, engineering visualization, reinforcement, and a lot more. Okay, so first thing, on the left I've got rhino. I'm just going to draw a line between 2 points. If I do distance on that, you can see that's 6,000 millimeters or 6 meters. But I'm just going to draw another random line as well, just to test. Then on the right, I'm going to bring those into rhino with curve. Just select them in rhino and say set multiple curves. So I've got those two curves brought in. You can see them highlighted in green. Now I want to start working with the curves, so I want to get the lengths of the curves. I know that first one was 6 meters. And if I use this component here, length under curve, that tells me 6,000 and 2,656. But what I'm going to do with that is I'm going to put that into a number component. But I actually do want it in meters, so it's in millimeters. So a very quick way to do that is use an expression here on this number component, and I'll say x divided by 1000. So that will give me 6 and 2.656, so that's in meters. Now the second thing I want to do to start drawing my diagrams is break the curves up into sections. So I'm going to use curve division, and you've got a few options here. You can set it, you can divide it between preset points or set lengths, but I'm going to use equal length segments because that makes the most sense for me at the moment. Now the n here is the number of segments, and 10 seems to be pretty good, but you can change that if you want, obviously. Now the next thing is I'm going to use the T component. Now to see what the outputs are, the quickest way is to just get a panel. And you can see that for the first curve and the second curve, it's split it up into these lengths. So these are obviously in millimeters again, so I'm going to use the same trick as I did before to make that into meters. So these are the lengths of the segments that I've split it into. Now, the first diagram I'm going to do is shear. Now to start drawing the diagrams, I'm going to use maths expression because I know the formulas to draw the diagrams. So I'm going to use this expression. Now I'm just bringing that in. Before I go into it, I'm going to set the variables, and if you zoom in Grasshopper, you get some additional options. So firstly, I need another variable, so I'm going to add one. I'm going to use X, because that's the way a lot of engineering formulas use their notation anyway for the position along the beam. I don't need Y in this case, but I'm going to call this W, and that's going to be my uniform distributed load. And I'm going to use this one as L, which is length of the beam. And they're pretty common engineering notation. So obviously we already know L because we've worked that out before, so I can plug that straight in. Now it's going red because it's confused because I haven't set these values. But before I go in, you've obviously probably guessed that X is all the different points along the curve that I've calculated already as well. So I can plug that in as well. W is going to be our load. So to do that for now, and the simplest way is just to set up a panel for your load. Now there's a lot of different ways you could do this, and I might suggest some of these later. But for now we'll just use the panel, and I'm going to use it in kilonewtons per meter, which is common in Australia at least. And I'm going to say 10 kilonewtons per meter. Plug that in. Now we need to go into that formula, clear all that out, and the formula to determine the shear diagram is W by length on 2 minus X. Easy as that. And this R will give me a set of results. So the next thing I want to do is start drawing that in Rhino so I can see the output. But to do that, I'm going to scale those results up because they're pretty small. If I have a look at them in the panel, they're sort of like 22 to 46 max, 50 max. I'm probably going to need it a little bit bigger than that, so if I use a slider, number slider, and I just double click on it, and I'm going to set the max as 100, and I'm going to call it scale. Then I'm just going to multiplication, put that scale into the bottom, put R into the top, see the panel results. If I move that up to about 20, I've got 1,000 there, which is about equivalent to about 1 meter, and remember this is 6 meters, so that's about a 1/6 high. So if I turn that into a Z height with Z, unit Z, plug that in there, and then finally I just want to get all of these points and move them up by the Z I've already calculated. So I'm just going to use move here. I know the transformation vector is the Z vector I've calculated, and we've got the points. Now it's started to plot my results there, however it doesn't look correct, and it isn't. You can look at the numbers and see that they're not correct either, because the shear force should be equal on either ends if it's simply supported, and 0 at the middle. And the reason it's not working is because of the way the lists are input into this component, and it's easy to fix. So what's happened is if you have a look at the inputs of this component, I've got two lists coming in, I've got a single number coming in, and I've got two numbers coming in. So what it's going to do at the moment is it's going to multiply each item in the first list by the first number, then the second number, then the first number, then the second number. But what I really want to do is make this list into the same format as that. So it's going to multiply, I want the same format. I want the 0, 0 and the 0, 1 in the L, so that it multiplies the lists instead of a list times a series of numbers. So an easy way to do that is just to graph this. You can see now I've got two lists which are identical, so it's going to take each list separately and multiply them together, and it's going to multiply them by the single number every time because it's just a single number, so you can't go wrong there. And you can see those results look much better, what you'd expect to see for shear force on a simply supported beam at each of those locations. Now if I want to make that a bit more clear, I'm going to draw some lines from these points, and the easiest way to do that is to use a polyline. Polyline here, connect a series of points. Oops. So that gives us a line of the top of the curve, and then I'm also going to join the points, which is a common way you see in textbooks. So I'm just going to use line between 2 points. I know one point, and I know the other point. And then finally I'm going to create a surface there, and I'm going to use loft. So if I go to surface, freeform, there's loft, create a surface between a set of curves. I know my first curve, and I know my second curve. Now I'm obviously going to have the same, I've got the similar problem as I had before, in that this is a list of two items and this is a list of lists. So I'm going to make this into a list of lists. And it's still not working because you can see, just go to the inputs and you can see the numbers in the lists are in a different format of the tree. So I need them all in the same format. I've simplified this, so I've got 0 and 1. My other input is 0, 0 and 0, 1. So I've got to simplify this also. And there you can see my plotted shear force diagrams. And you can change the scale to see the results. Right, so now I want to do the same thing, but I want to get the bending moments. So I'm just going to copy and paste that. So the formula for working out the bending moment at each of those points for a simply supported beam, I'm just going to write over this one, is, and I'll just set it up into brackets to make sure it's definitely going to work the way I want it to work. W times x on 2. I bracketed that off, multiply that by, open a new bracket, L minus x. So let's see what this gives us. there's your bending moment diagrams. And again, I can scale them as I need to. And I can see the results in this panel. In a minute, I'll put a result here so you can see it on the screen as well. I'm just going to turn off some of these points because I don't think we really need them. You can keep them if you want, but I'll just turn them off. So we've got our shear and our bending moment. Now I'm going to do deflection. So pretty easy again, I'm just going to copy and paste that. Now for this one, obviously for deflection you need an E and an I value. Because this is a simple tutorial, I'm just going to combine them as an input. I'm just going to copy and paste this. I'm going to call this EI. Now, as an expansion to this demo, you could come up with different ways of putting EI in for different beam sizes. But just to keep this demo quick, I know an EI in terms of meters and kilonewtons for a 200 UB18, I think it was, is 2.239. So I've put that into the formula so it's ready to go. And then the formula is going to be, I'll clear that away. I'm going to have minus so that it goes down. Obviously it's going to deflect downwards. W times X over 24. Oh, sorry. I need to open a bracket times 24 times my EI value. And then all of that I'm going to multiply. It needs to be multiplied by, in brackets, L to the power 3 minus 2 times L times X, and X is to the power 2, plus X to the power 3, close bracket. Let's see what that result gives us. That's our deflected shape for this load, and the span is worked out automatically by the script. And again, we can scale that. So interestingly, you can see the shorter span makes a bigger difference to the deflection than it does to the bending moment diagram, which you'd expect. And if we go back to deflection and have a look at the results, whoops, we got 52 mil there and only 2 mil on the little one. Now what happens if we just want a simple way of flicking between shear, bending and deflection plots without having to disconnect and reconnect to this multiplication component? So I'm going to do that quickly by setting up a value list. I'm going to edit that. I'm going to clear that away, just keep the first one. I'm going to say the first one is shear. Copy that. Paste. Bending is the second one, and that will be 1. And deflection is the third one. That'll be 2. So 0, 1 and 2 in a list. Now I've got my results all ready to go. So I'm going to set up a number to hold it all, and I'm going to put them all into that number, and I'm just holding down Shift to add those results. So it's not in the correct format, as you can see, because I've got 11 results for each, and it's put them into 2 lists, and each list corresponds to a beam. So what I actually want to do is graft all of these, and what that does, it's wrecked my current graph, but I'll just disconnect that for the moment. So it's put them all into a simple, it's put every list into its own list. But what that means is when I combine them into 3, each list has 3 items because I've got 3 inputs to it. So now I can choose between the 3 items if I use list item, because for the 3 items they'll have an index of 0, 1 or 2, and we've set up as an index of 0, 1 or 2 up here. So if I combine that, this will just be shear, and that will just be bending. So I can simply just put this result into that component there. And now that I've put that in there, it's not quite working. And why is that? Again, a lists thing. So I've actually got to trim this list, and what trim does, trim tree, it reduces the complexity by merging the outermost branches. So if you have a look at these results, I've got 0, 0, 0, 0, 0, 1, and then it goes to, that goes up to 10, and then from 1 to 1 by 10. But what I actually want is to get rid of these outer branches and just have 2 lists like I originally did. Got 2 lists inputting into this move, and I don't want 22 lists because that's what it's trying to graph here in Rhino. I just want 2, except I want to trim not at this point, which gives me 33 results, because I want to choose from the 3 of this number, so I want to trim after the item. That was a mistake there. So that gives me 11 results in each list, is which I had previously, so that's exactly what I want. And there you go. So now I can select shear, bending or deflection just with a drop down list. Okay, now the last thing I'm going to do, which is have a quick way of showing the results in Rhino rather than just reading them off a list like this. And for that, we're just going to tag the results using text tag. And for that, we need a location and the text. The color you can set if you need to. So to do that, I want to find the worst results in each case. So for that, I'm going to use the sort list component, and I'm going to sort these results here. I'll just rearrange this a little bit. So the thing I want to sort is the results, and I want to keep the location of that result also in the same order as the list that I'm sorting. So the location is up here, So the A is values that it sorts in the same way that it sorts the keys. So if I just unpreview that, I don't really need to see the points. I've got my list of results, so let's have a look at that in the panel. It's gonna sort them from most negative to most positive. And what I need to do is grab the highest and the lowest value. So obviously if they're sorted, that's the first item and the last item in a list. Now a quick way to do that in Grasshopper is to use this shift list. Put the list in there, and I'm going to shift by -1. Then I'm going to use list item, and I'm going to add a parameter here. So this gives me the first 2 points. So if I look at this shifted list, I've got the lowest most point and the highest. The lowest value is actually the first result, and then it's shifted the list from the highest result being 10 in index 10 to the highest result being in index 0. So all this means is that I've got a list with the highest and lowest in the first 2 spots, and this item is going to give me the first 2 spots. Now to make it look a bit nicer as well, I'm just going to round these numbers up. And I'm going to put them by holding down shift into round. You've got a few options, floor and ceiling, but I'm just going to use the nearest integer. And I'm going to concatenate that with a panel. I'm going to use kilonewtons for shear, kilonewton meters for bending, and millimeters for deflection. And I've got to make that a multi-line data list so that I've got index values for each. Because, again, if we grab a list item, I know those indexes from this drop-down menu. And I plug that into the list. So it should give me millimeters for deflection. Yeah, I'm on deflection. If I go to bending, should give me kilonewton meters. And I should have said, I want to add a space in front of all of these, because that result, the number that I've got given, if I plug that into there and plug that into there, what's that going to give me? 45 kilonewton meters, 0 kilonewton meters, 9 and 0. So it looks pretty good. That looks good for my T, which is the text to display. And then finally, I've just got to tell it where to put that result on the screen. So again, I'm going to use the same method. Copy and paste the shift and the item selection, but I'm going to use the A, which is the location of each of these. And I'm going to use move. Well, before I do that, actually let's put it into move, and then put that into location. There you go. Just unpreview that so you can see, and unpreview that and that. You can see the results, but I just want them a little bit higher. And there's an easy way to do that. Just say Z and set a number of, so the first result will be the lower, so -100, and the next result will be +100, because that will be the higher result. Put that into there and that into there. Oh, whoops, I've done it the wrong way around. So that one there and shift that one there. There we go. So now if we, it'll work with shear and deflection and bending because it's just working out the highest and lowest points. Shear, bending, deflection. And it tells you the units as well. And obviously I can just draw some more lines in if I need to. And for example, you could do beams in a these could be they could be the columns, for example, and then you've got an intermediate beam. And I could just select those curves. And it's going to tell you the shears, bending, and deflection of each of these. Obviously, these are all the same load and all the same beam size for the moment. So an extension, there's a lot of ways you can improve this, make it a bit more complex. You could set up a way of working out what the amount of load coming onto it is. A way of doing that might be to draw a box, then work out how much area is going into this beam, and then multiply your load by that, your W. Or another way to improve the script would be to have a selection of beams, and it just inputs EI, and then you can just flick through your beams, change your beam sizes. And obviously you can select different EIs for different beams if you want. Thanks for watching this structured parametrics video. Leave a like or subscribe if you found this useful, and we'll see you in the next one.